Now, the critical position for shear on a normally loaded flexural member is at the support, where we have maximum reactions, where we witness maximum reactions. Now, the shear stress occurring at that position is calculated and compared with the permissible value. For rectangular timber flexural members, the maximum applied shear stress parallel to the grain RA occurs at the neutral axis and is calculated using the following formula. That is, RA is equal to 3 times the shear force divided by 2 times the cross-sectional area. All right, so again, just to look at the formula again, what we can see is FV, that is the maximum vertical shear force, right? This is in kilonewton, right? Then basically the shear force is the maximum reaction at support. Capital A is the cross-sectional area, and for a rectangular section it is B times H or B times D. The applied shear stress must be less than the permissible shear stress parallel to the grain or ADM. All right, so this is something we have to ensure. All right, so this is about the shear. Now, the shear stress parallel to grain should be less or equal to the permissible shear stress parallel to grain. Now, the permissible stress parallel to grain is obtained by multiplying the grade shear stress, right? So the grade shear stress should be multiplied by the respective modification factors, K3, which is the modification factor for load duration, and K8, which is the modification factor for load sharing. So this is how we obtain the shear stress parallel to grain, which is permissible. Now, notches occurring at the ends of flexural members affect the shear capacity. Now, many times, because we've got to join the horizontal to the vertical members, we might have notches occurring at the end. Now, we've got a reduced section at the ends. Consequently, the shear is affected. The shear resisting capacity is affected. For a bigger section, you can offer more shear resistance compared to a thinner, smaller section. To allow for notches, that is the reduced resistance to shear, the permissible shear stress parallel to grain is further reduced by a modification factor K5, right? So now the shear stress parallel to grain, which is permissible, must be multiplied by K5. And this is the last formula provided on this slide should be used as the final formula to do the check for shear stress. Now, the factor K5 is obtained in one of the following two ways and depends on whether the notch occurs in the top or bottom of the member. All right, so this is very important. So figure 2.1 shows the notch occurring at the top of the member, while in figure 2.2 you've got the notch occurring at the bottom of the member. All right, so for top edge notches, we have to use this particular formula, all right? And for bottom edge notches, K5 is simply taking the effective height divided by the normal height of the section, okay? Whereas for the top edge notches, you have to follow the formula and use the values provided there. All right, for example, h is the original height of the section, he, the effective height. All right, once you remove the notch, you've got an effective height, and this should not be less than 0.5 h. So you have to make sure that this condition is entertained. You've got A, which is the extent of the notch beyond the edge of the support, right? And you just use the formula as is. Okay, again, just to emphasize again on the height, the effective depth HE of the timber you're designing should never be less than half the member depth. This is important and should be maintained at all times. It should be noted that the area used in the expression for calculating the shear stress parallel to grain at a notched end is the net area after notching, that is A is equal to H is equal to B times HE. So the area is important, so you have to take note of that and use it accordingly.